A developer builds a private coding assistant. The source files go into object storage, metadata goes into a relational database, embeddings go to a vector service. Keyword search becomes another service, a re-ranker becomes another API. Then every question travels through 5 systems before the model can answer. For many projects, that entire retrieval stack can collapse into one SQLite file. Not every project, and not with vector search alone. The useful design is hybrid retrieval, exact words, semantic similarity, metadata filters, and normal relational joins working together. Start with the failure of keyword-only search. Suppose the user asks, where do we refresh a login session? The code may use the phrase rotate access token. A strict word search can miss the concept because the wording differs. Now try vector-only search. Embeddings can connect refresh session with rotate access token, but they can be weak at exact identifiers, error codes, version numbers, or a function named refresh_session. Developers need both. SQLite already has FTS5, a full-text search extension. It supports phrase queries, prefixes, proximity, Boolean logic, ranking, snippets, and highlighted matches that handles exact language and code-shaped terms. The sqlite-vec extension adds vector columns and nearest neighbor queries through SQLite virtual tables. It can store floating point, 8-bit integer, and binary vectors. The project is written in C, has no runtime dependencies, and is designed to run anywhere SQLite can run. Now the retrieval pipeline becomes local. One table stores each chunk of source text. Normal columns store file path, language, repository, commit, symbol, and access scope. An FTS table indexes exact content. A vector table stores the embedding connected to the same row identifier. At query time, the application generates one embedding. It runs a full-text search and a vector search. Then it combines the candidate sets, applies metadata and permission filters, and re-ranks the small result. The model receives a few source-backed passages instead of an entire repository. This has 4 major advantages. First, consistency. The content, metadata, and vector reference can be updated inside one database workflow. You avoid a relational record saying one thing while a remote vector index still contains yesterday's chunk. Second, filtering. Because the metadata lives beside the retrieval data, normal SQL can restrict results to one repository, branch, customer, file type, or permission scope. You do not need a separate filtering language that almost behaves like SQL. Third, privacy. A local application can keep source text and embeddings on the same device. That does not guarantee privacy. The embedding model and application still matter, but it removes a network hop and an external database account from the core search path. Fourth, deployment. One database file can be copied, backed up, inspected, and shipped with the application. For a desktop assistant, command line tool, edge device, test fixture, or small internal service, that simplicity is enormous. Now the complications. The sqlite-vec project explicitly describes itself as pre-version 1 and warns users to expect breaking changes. That is not a reason to ignore it. It is a reason to pin versions, test migrations, and avoid designing a critical production contract around an unstable interface without a recovery plan. SQLite also has a concurrency shape. Write-ahead logging can let readers continue while a writer is active, which is excellent for many applications. But SQLite is not a magic distributed database. It does not become a multi-region cluster because a vector extension was loaded. One file also means one failure domain. You need backups, you need integrity checks, you need a strategy for rebuilding embeddings when the model changes, and you need to understand how large the vector index becomes as documents multiply. The retrieval algorithm matters too. For a small or medium corpus, exact or near-exact vector scanning can be fast enough and wonderfully simple. At very large scale, approximate nearest neighbor indexes and distributed query systems may reduce latency dramatically. Heavy concurrent writes, billions of vectors, strict high availability, and complex multi-tenant operations are signs that dedicated infrastructure may be justified. So here's the decision boundary. Use SQLite hybrid retrieval when the application is local first, single node, privacy sensitive, embedded, easy to rebuild, or modest in corpus and traffic. It is especially strong when relational metadata and exact search are as important as vector similarity. Use a dedicated vector or search service when the corpus is enormous. Traffic is highly concurrent. Multi-node availability is mandatory. Operational teams already support the platform, or advanced indexing and filtering performance justify the extra system and do not begin with scale anxiety. Build a representative corpus record database size, test indexing time, measure full-text latency, vector latency, and the combined re-rank. Evaluate retrieval quality with real questions. Then increase the corpus until the service level target breaks. Quality matters more than a pretty latency chart. Create a test set with exact identifiers, paraphrased concepts, rare error messages, and permission boundaries. Compare keyword-only, vector-only, and hybrid results. In developer tools, hybrid often wins because code contains both natural language and rigid symbols. Hybrid ranking does not need to be mysterious. Give strong exact matches a text score. Give semantically close passages a vector score. Normalize both lists, add a recency or repository prior only when the product requires it, and re-rank the small merged set. Keep the scoring receipt during evaluation. When a bad passage wins, you should be able to see whether text, vector similarity, or metadata caused the mistake. There's also an important security rule. Filter by authorization before content reaches the model. Do not retrieve everything and ask the language model to ignore forbidden rows. Permission is a database constraint, not a prompt suggestion. So the minimal architecture is this: one content table, one FTS index, one vector table connected by stable identifiers, one query that gathers keyword and semantic candidates, one permission and metadata filter, one re-ranking step, and one evaluation set that proves the answer cites the correct source. That is not a toy architecture. For the right workload, it is a reduction in moving parts, network hops, bills, and failure modes. SQLite will not replace every vector database. It can replace the reflex that every embedding requires a new cloud service. Start with one file. Add infrastructure only when measured scale, availability, or operations demand it. Simplicity is not the absence of engineering. It is engineering that has not invented a distributed problem before the workload exists.